This conference will now be recorded.
So good morning to all the students. Hope everybody is doing well. And so today, as we were continuing discussing liquid extraction, and let us continue that. So as all of you know that the liquid extraction is also called by name of the solvent extraction. And as I have already explained in the last class that there will be a feed and in which you have a solute in which you are interested to separate, and you will add another solvent which is called extract solvent. So both will be mixed here, and one phase will be dispersed in another phase, and during that one of the component which is called common solute to the feed solvent and extract solvent will be exchanged by those things, and then later it goes to the settler. In the settler, due to the density difference between the phases, you will find two phases will be settling one above another one, and we can separate them into the two different fractions. So usually the aqueous acids are being separated by solvent extraction. So that's why we call one of the phase is aqueous phase and another phase is organic phase. Usually organic solvents are used. And in industrial terminology is that feed solution, and which is heavy in density, and organic solvent is light. So light phase and heavy phase we call by that name. And finally you will get the extract phase and raffinate phase. So extract phase is having more solvent, and the raffinate phase is having the feed solution which is treated with the solvent. So you find less solute at the end, and some of the solute is getting transferred into the extract phase. So this is the overall operation in which you should have one mixture and one settler. So one stage refers one mixture and one settler. Usually we represent this one in a ternary diagram because there are three liquid components. So that is A, B, C. So usually you get a binodal curve, as I have explained in the last class, that there will be a flight point, and flight point is analogous to your isotropic point in the vapor liquid equilibrium. So here also you have no chance of separation at a flight point, and that is also called the single point tie line, because this tie line represents the equilibrium stages, and the below the curve you have heterogeneous phase. Outside of the this demarcating curve we call the homogeneous phase. So any point you take uh, under this curve, then that tends to separate into the extract phase as well as the raffinate phase. So this indicates that the separation is only easy when you bring the mixture of the three components into the this phase. So you have a three type of systems in liquid extraction. One is one immiscible pair. So that is the carrier and solvent will be the immiscible, and the remaining are partially soluble. So if you take the water, chloroform and acetone, you find this type of system. So in which you find one plate point and also tie lines, and this curve is called either equilibrium curve or a binodal curve. So another type of system is two pairs are immiscible, that is chlorobenzene, water, and methyl ethyl ketone is an example to form this type of ternary diagram. So here it indicates that there are two A and solvent, the solute and solvent, and carrier and solvent. Carrier means it is also called a feed. This feed is carrying the solute, so that's why it is called a feed solvent, and this is organic solvent. So these two are partially miscible, and solute and solvent also partially miscible. But whereas you find the solute and carrier solvent, feed solvent, is completely miscible. So this is an example for two immiscible pairs. This is example one immiscible pairs, or two partially soluble pairs. So on this, because here you don't find the tie line, tie lines are in a different manner. You don't find the plate point. So what you do is you increase the temperature of the system so that this type of useful binodal curve appears here with one flight point. So in normal condition, if you don't find the flight point, then you have to increase the temperature so that the solubilities of three components in each other enhances at higher temperature, and you will get this type of uh, like binodal curve. So this type of binodal curve is usually useful. And also you can draw different type of equivalent diagrams like VLE diagram. This is also called LLE diagram. You can use the ternary diagram or ternary graph in which equilateral triangle will have a equal parts, and then the three component compositions can be taken, and you can see that you will be having this type of tie line. Or you can also use a rectangle coordinates, that is a uh, right angle triangle also you can draw. In the right angle triangle, what you can take is xy. This is the weight fraction of the C. X indicates in the raffinate phase the weight fraction of the C, and in the extract phase, weight fraction of the C is indicated by Y, and X and Y will be taken on, the Y axis, whereas on X axis we have to take the weight fraction of the B. What is B? B is the organic solvent which you are intentionally adding. So when you add at less quantities, you'll find the raffinate phase, and when you add more, then you find the organic phase. What you have to do is, you see, when you are adding certain quantity of B with the feed mixture of A and C, then what happens, and it may have a homogeneous phase, and while you are go on adding the B, then the homogeneous phase will be turned into the heterogeneous phase that you can observe. So that point you have to note down. So where exactly it is turning to the homogeneous to the heterogeneous, homogeneous will have no turbidity in the solution, and when the heterogeneous started forming, then you can see a oily nature, that is the turbid, in the solution. Therefore you can see that that is the starting point of the heterogeneous phase. Like that you can draw these lines. So this line is called again binodal curve. Instead of this ternary graph, you can draw this on ordinary graph by using the xy coordinates. So that's why it's called right angle triangle coordinates or rectangle coordinates. So you have here x and y on y axis, and then the weight fraction of the B in the solution. That means weight of the solvent which you have added divided by the total solution weight. So that gives the weight fraction of the solvent which you are intentionally adding, extracting solvent. So you will get this. So a similar type of curve can be reproduced in the ordinary graph that can be used, because this drawing the triangle diagram is a little difficult. Then you can draw in this. And similarly, you can also draw the diagrams by using solvent free coordinates. I will tell you what is the solvent free coordinates. So here n, you can find out the n. What is the n? N is weight of the solvent, organic solvent, on solvent-free basis. What do you mean by solvent-free basis? In denominator, the cases of A and C will be taken in which B will not be included. So that is the definition for N. So N may be there in the raffinate phase. So raffinate phase N values will give like this. And in organic phase, because organic phase weight of B will be more, then you will get this type of curve. So this is the N in the organic phase. This is N in aqueous phase. So N in aqueous phase versus the another X value. What is the X value? X value is the weight fraction of the solute on solvent-free basis. How do you calculate? A-rich solution means aqueous solution. A is the feed solvent. So how do you calculate X? Weight of the C. C is the solute. Weight of the C divided by weight of A plus C. So B will not include. So that's why it is called solvent-free coordinates. So X will be calculated the weight fraction of the C in the A-rich phase without adding the solvent, and Y is also calculated on solvent-free basis. How do you calculate the Y? It is weight of the C divided by weight of A plus C in organic phase. Organic phase is the B-rich phase. So that gives this type of diagram. So this is XY and N and XY. So this is like it is analogous to the your HXY diagram, which has been used in Panchin-Savarat method. And again you see here a single equilibrium point will give you one tie line on an XY diagram. And this single equilibrium point again will give the NXY diagram. So NXY diagram are the right angle triangle diagrams or ternary diagrams are usually used to estimate the required parameters in liquid-liquid extraction. Okay. Then here one must understand that the selection of the solvent. How do you select? Because we may have so many solvents in which the solute which you are interested to separate from the feed. For example, if you take acetic acid which is there in the water, to separate acetic acid you can use either chloroform or benzene or chlorobenzene. So like that there will be three different solvents can be used. But the question is that which solvent is best choice. So to find out that there is a criteria, one should go through that criteria. There are certain parameters. One should estimate those parameters, and then you can take a decision that is this solvent out of 1, 2, 3 or B1, B2, B3. The B2 is best or B3 is best or B1 is best. So such decisions can be taken once you go through the criteria. In the criteria, the first parameter one should estimate is selectivity. So what is the selectivity? The effectiveness of the solvent B for separating a solution of A and C into its components is measured by the comparing the ratio of the C to A in the B-rich phase to that in the A-rich phase at equilibrium. For example, if you take a solution and in which heterogeneous phase is observed, then if you wait some time, this heterogeneous phase will be settled into the two different phases. Then if you separate, then you will get the two different phases. One is called A-rich phase and another is called B-rich phase. Or you can also say extract phase, that is E, and raffinate phase, that is R. So you can estimate the selectivity by using this equation. What is this? Weight fraction of the C in E. E means extract divided by weight fraction of the A in extract. A is what? Feed solvent. For example, if you have water, acetic acid and chloroform, then the E is chloroform, A is water, C is acetic acid. So weight fraction of the C in E divided by weight fraction of the A in E, and whole divided by weight fraction of the C in raffinate and weight fraction of the A in raffinate. So this is pertaining to the extract phase, and this is pertaining to the raffinate phase. So this beta is the ratios of the compositions of the solute in the extract phase as well as in the raffinate phase. So that can be simplified in this fashion: Y star by XR, because these two are in equilibrium, and weight fraction of A in R divided by weight fraction of A in extract. So if you take this one, then the beta, that is the selectivity, can be estimated. For example, if the beta is, hello, who is this? Hello, please mute. Hello, please mute all. Yeah. So this beta is analogous to the relative volatility value. Relative volatility. How do you define the relative volatility? If you remember, relative volatility alpha is equal to y by 1 minus y divided by x by 1 minus x. So this is having in a same definition. So therefore, beta is analogous to the alpha, relative volatility. Then you can see that usually weight fraction of A, for example, A is the feed solvent, A doesn't go into the extract solvent, because we should select A, you should select E such that A should not be dissolved into that. So if it is dissolving very less, and see, this value will become very low. Therefore, beta will become very high. Or sometimes, if no A is going into the extract, and this will become 0, then beta goes to the infinite. So that is the more useful. More beta value will be very much useful to us. If the beta is much greater than 1, then the separation will be very easy. If the beta is equal to 1, what do you mean by that? Beta is equal to 1, and you can see that weight fraction of A in R and weight fraction of A in E will be typically equal. Therefore, these two also will be equal, and beta will become 1. When the beta is becoming 1, then there is no separation possible. If the selectivity value is needed to the 1, then, or it is equal to 1, then you can get heteroisotrope. There will be two layers together in the solution, but each layer will be having all three components compositions equal. That means the system is called heteroisotrope. So if heteroisotrope is there, when beta is equal to 1, then the separation is not possible. So you have to select the E such that A dissolves less, and as well beta value will be more. So selectivity will give you one parameter how the solvent can be chosen. Then the second one is the distribution coefficient. And see, this distribution coefficient, as you have already defined in the equilibrium of vapor liquid, where the K value, equilibrium ratio, is Y star by X. Similarly, the distribution coefficient is the ratio of Y star by X. That means at equilibrium, Y star by X. So this ratio is called the distribution coefficient. So distribution coefficient is the ratio of the solute concentrations in the extract phase to the raffinate phase. So the distribution coefficient value is not necessarily that be larger than 1. It need not be larger than 1. Even it is 1 also, but if this difference is there, then the beta value may be greater than 1, then the separation is possible. So even distribution coefficient is 1, So you may get the certain separation, but however, the larger values are very desirable since the solvent consumption will be very less for the extraction. So if you have large distribution coefficient values, then the solvent requirement for the separation will be less. So this is regarding the distribution coefficient. So one is the selectivity, which you see whether it is greater than 1 or not, and another one is distribution coefficient, that you will see it is very high or low. You rate and the consumption both can be compared later, because distribution coefficient is very low but rate is cheap, means even though it is consuming more, you can go for that type of. But if the distribution coefficient is very high and it consumes very less, but the cost is very high, means then there is no uh, necessity of choosing that particular solvent. So this will also help. Distribution coefficient parameter also will help us to take a decision whether you can use that solvent or not. So another one very important parameter which you should see in the choosing of the solvent criteria is insolubility of the solvent. For example, if you take A and B diagrams which are shown here, and A diagram will have is having more binodal curve loop, and B diagram is having very low binodal curve loop. So out of the A and B, if you see the C is, for example, if you take a solvent B and here B prime, so the C solubility in the B will be very less when you compare to the C solubility in B prime. So that is called insolubility. So this diagram is having C insoluble in the B. Insolubility of solvent will give the more binodal curve area. More binodal curve area means more heterogeneous zone. Less binodal curve area means more homogeneous zone in the solution concentration ranges. So see that D to B prime. So this indicates the solubility of the C in B prime, and DCB indicates the solubility of C in the B. So it is having a less area, this is having more area. So less area will be prepared than this because it shows more binodal curve area. So this required, this requires. So instead of B prime and B, by seeing the binodal curve areas, by knowing the insolubility of the solvent, you can select this one. However, insolubility of C in the solvent will incur larger consumption of the solvent. So that also you should see. For example, if you select this solvent than this solvent, so this solvent requirement will be more for a fixed separation, but it is useful. Insolubility is useful than this one because this gives the more homogeneous zone. Even the solvent consumed is less in this case, but we'll go for this one. So that is how insolubility of the solvent will affect the liquid extraction. So you should see while you are choosing the solvent, this type of binodal curve is more preferred. Then another one is recoverability. For example, A, B, C. So A is having C initially. Now the C is entering into the B, and from the A phase it is entering into the B phase. Now from the B phase also you have to remove the C. So how to recover the solvent? Recoverability will be very easy. So you should see that it is always necessary to recover the solvent for reuse, because solvent you have to reuse, the B can be separated and sent back. So this must be ordinarily be done by another mass transfer operation, most frequently distillation. So to recover the solvent, distillation is used. If the distillation is to be used, the solvent should form no azeotrope with the extracted solute. So whatever solvent you are adding, that should not form the azeotrope with the solute. If it is forming the azeotrope, means again the separation is very difficult. So mixtures should show high relative volatility for low cost recovery, and also high relative volatility should be there. The substance in the extract, either solvent or solute, which is present as the lesser quantity, should be the more volatile in order to reduce the heat costs. If the solvent must be volatilized, its latent heat of vaporization should be small. So these parameters are to be kept in mind because it directly involves in the recovery of the solvents. So you should see that. What are those things? It should not form azeotrope, and also high relative volatility to reduce the heat costs. So these two parameters should be seen. That means solvent must be volatilized very easily because its latent heat of vaporization is very small. So you should see these parameters, physical parameters, while you are choosing the solvent. So another very important, this will be useful in the settler, density. So a difference in the densities of the saturated liquid phases. After reaching the two liquid phases equilibrium, we call the two phases have saturated with the solute C, then we call them as a saturated liquid phases. So a difference in densities of the saturated liquid phases is necessary both for stage wise and continuous contact equipment. So you to have a batch process or continuous process, the density difference is should be very high. The larger the density difference, the better. In the systems, the density difference for equilibrium phases will become less as the C concentrations increases and will be zero at the plate point. The density differences will be zero at plate point. It may reverse in sign before reaching the plate point, in which case continuous contact equipment cannot be specified to operate at the concentrations at which the density difference passes through zero. So at plate point, you should understand that the density difference will be zero. Therefore, it is not possible to separate the organic phase and aqueous phase, or raffinate and extract phase. So you can see the density differences for equilibrium phases will become less as C concentration increases. When the C concentration increases, the densities of the two phases will come very nearer, and at plate point they will be equal. So you should take care of that. Then another very important in the mixing, interfacial tension. The larger the interfacial tension, the more readily coalescence of emulsions will occur. How the emulsions will form while one is dispersing in another. Usually, what is the notation which I know, which you know from the mechanical unit operations? When the low density, low density liquids are bound to disperse in heavy liquids because of their density differences. When they are dispersing one in each other, then there will be coalescence will form. So these coalescence will form and disperse. So the larger the interfacial tension, the more readily, if the interfacial tension is large, so the coalescence of emulsions will form very easily and more difficult. But the more difficult the dispersion of one liquid in the other. If the interfacial tension is more, then the dispersion will be less. So you should understand, if interfacial tension is more, then it is more difficult to dispersion one in each other. Because of the interfacial tension, they won't disperse in each other. So that affect the mixing. Then the coalescence is usually of greater importance, and interfacial tension should be therefore be high. However, interfacial tension between the equilibrium phases in liquid-liquid systems falls to zero at plate point. So interfacial tension between the two equilibrium phases should be high, should be high to form the coalescences, and also it will promote the dispersion. You should see that also. It should not be difficult. So such a organic phase has to be selected. Then the chemical reactivity. The solvent should be stable chemically, means whatever organic solvent which you are adding, that should be stable. It should not react either with A or C. That means feed solvent or solute. So the solvent should be stable chemically and inert toward the other components of the system and toward the common material of construction. This is the common material of the construction, means we have mixture and settler. So this mixture and settler, these two material of construction, because they are done in a particular equipment, so that material of construction of that equipment should not get either corrode or erode due to the solvent which you are adding. So it should be chemically non-reactive. Chemically it is non-reactive. Okay, then the viscosity, vapor pressure and freezing point. So these are the very important physical properties. So these properties are should be low. Why it should be low? Because the handling will be very easy and storage also very easy if the viscosity, vapor pressure and freezing points are low. Then the solvent should be non-toxic, non-flammable, and it should be available plentifully at low cost. So these parameters are to be carefully studied before selecting the solvent. Once you have a solvent and also the solute which you are interested to separate from the feed solvent, then you can adopt either single stage extraction or batch wise or a continuous mode. In a batch wise, you can take a mixture and add feed and solvent and mix and allow to the another settler. In the settler, maybe due to the gravity or due to the centrifugation, the two layers will be separated. So you will get a lighter phase and heavier phase, so that extract phase and raffinate phase can be separated. So in a continuous phase, the feed will be sent continuously at a particular rate, and also solvent will be added at a particular rate, and they will be mixing on they are traveling through the mixture. They form a turbulence, and one will mix in another one very thoroughly. Then they will be reaching to the another settler. So there they will be decantation may be done, or a centrifugation can be done to separate. So you will be obtaining in a continuous phase the E value and R value, extract value, raffinate value per at a particular rate. That means kgs per unit time. And in a batch, you will get after batch time kgs of E, kgs of R. In a continuous phase, you will get kgs per hour of E, kgs per hour of R. So these are the concentrations, weight fractions. XF is the weight fraction of the C in the feed, and YS is the weight fraction of the C in the solvent. If the solvent is fresh solvent, and for the first time you are using, then YS will be 0, and otherwise you see this lighter phase will be subjected to the solvent recovery, where you will be separating the C and B, then the B will be sent back. In that case, the solvent is coming from the recovery plant, so recycled one. Therefore certain YS will be there. That means certain solute will be there in that. So solute may be 0 in the solvent or very little quantity, because during the recovery the traces of the solute will be remaining in the solvent. So YS will be very low value. XF value will be very high. So both will come here and mix together. Then they will be entering into the settler. Then the lighter phase will have this much concentration of the C, and heavier phase will have this much concentration of the C. So YE and XR will be in equilibrium. So these two are in equilibrium, because after reaching the equilibrium only they will be separated. Okay. So in ideal stage also continuously they will be separated at a same rate, but YE and XR are assumed to be in equilibrium. So even though they are having two different unit operation, one mixture and settler, but this rounds shows that one mixture and one settler. So that may be a stage one. So you can send feed and solvent, and raffinate and extract will be obtained. So how do you find out? Suppose you know this much kgs of the feed having this much concentration of the solute will be treated with this much of the solvent, which is having ys value is very low or zero. Fresh solvent or solvent, when you are treating this feed with this solvent, and how much of r and how much of e will be obtained, and what would be the concentrations x1 and y1 in if you use only one stage. So this is the quantities of the raffinate, quantity of the extract. This is the quality of the raffinate and quality of the extract. So quantities and qualities in a single stage batch operation, in a single stage continuous operation, can be found out from the extraction principles. So in the extraction principles, you know that equilibrium will be attained in this stage. Means here, once the mixing is thorough, then you can assume that equilibrium is obtaining. Then the equilibrium phases are separated here. So these two phases are assumed to be in equilibrium if the stage is ideal. So first you do the total material balance. All of you know that once you have this type of operation where inputs and output, then the total material balance equation will give the relationship in the quantities of the phases. This is the quantity of the feed, this is the quantity of the solvent which are added, and this is the total mixture quantity in the mixture. After adding feed and solvent, this much of the mixture has resulted, and this mixture, if you allow to settle, that is divided into the E and R. This much of extract phase quantity, this much of the raffinate phase quantity has been separated. So this gives the total material balance. What is that? F plus S is equal to M, and that M is equal to E plus R. So this is how you will get the total material balance equation. Then the solute balance equation. What is a solute? Solute is the one of the component in the feed, as well as feed will be dissolving into the solvent, and which will be there in the extract phase as well as raffinate phase. The solvent may have C or may not be having solute. So when you do the solute balance, then you have to multiply the quantities with the qualities. Then the feed into its composition, solvent into its composition should give the mixture and its composition. See, this mixture is not homogeneous mixture. The feed is homogeneous, the solvent is homogeneous. When you add the feed and solvent, then the mixture M is not a homogeneous phase, it is an heterogeneous phase, and it will have this much concentration of the solute. So mxm, how do you calculate the xm? Xm can be calculated feed into the feed composition plus solvent into solvent composition divided by M is the combination of the feed quantity, solid quantity, weight of the feed plus weight of the solid. So you will get the xm. So xm is the concentration of the solute in a heterogeneous phase. This heterogeneous phase cannot be stable for the longer period because it will divide into the E phase and R phase. Then this is the another equation which can be generated. The E into YE, E quantity of the extract phase generated from this mixture, and YE is the quality of the or weight fraction of the C in the extract phase. So this will give you that C contained by extract phase. Then R into XR will give you the C contained in the raffinate phase. So E phase is a stable phase, R phase is a stable homogeneous phases. M is not a homogeneous phase, it is a heterogeneous phase. So combining these equations, then you may get F by S is equal to xm minus ys divided by xf plus xm. So you will get this equation. Usually this is the ratio of the feed to the solvent will be measured by this one. Okay, now it is very important for us to estimate E, R, YE, XR. How many parameters are there? 1, 2, 3, 4. 4 parameters are there, but we have only 2 equations. So 2 equations, 4 parameters. So you don't uh, find any solution for the 4 parameters having a 2 equations. So you want one more relation. That relation is the equilibrium relation. So equilibrium relation will give you this one, binodal curve. So this binodal curve will give you what would be the homogeneous zone, what would be the heterogeneous zone. For example, if you, this is the feed, you see, this height indicates, xf value, because if you go vertically to this apex of the peak in an equilateral triangle, then starting from C0, you are reaching C100 here. So on this line, C is 0. So if you go vertically like this, then XF will come out of the 100%. How much percentage of the C is there in the feed will give you this point on this side of the equilateral triangle. So here you will get the F value. So this F is the feed, and this height indicates the concentration of the C in the feed. So you will get the F. Then this F, and now the solvent. Coming to the solvent may be the 100% B, that means pure solvent, or traces of YS will be there. If it is a pure solvent, this corner of the equilateral triangle is the solvent point. So it indicates 100% solvent. There is no C or no A. If certain traces of A, certain traces of the C is there, this point may go a little up and it may come here. So what is happening in the mixture? In the mixture, you are adding feed with this solvent. So you will get this one. This is called a mixture operating line. In the mixture operating line, when the feed and solvent are added, and the concentration of the C, initially this is the concentration of the C, will come down because it is making dilute with the solvent. Upon the addition of the solvent, the feed is getting diluted with respect to of the C composition. So C composition falls down to a value of this one. This is the XM. How do you find out this XM value? The XM value can be found out F into XF plus S into YS divided by F plus S. So after drawing this line, find out XM and then identify this point, M point. Now M point will be splitting into the two equilibrium phases, E phase and R phase. So you have to draw one tie line which goes to the M point. So you have a different tie line points and see that trend of the tie line and draw one tie line which goes through the M point. So how do you draw this tie line? For example, I will tell you, see, these are the tie lines, see, isn't it? For example, if you have a M point here, so just draw one vertical line here and take this and take this ratio, and the same ratio can be maintained here and here also. Then add these 2 points through the M. Therefore, the tie line can be drawn. So you have to draw one tie line, which is a very carefully you should draw the tie line by seeing the different tie line trend. You have a number of tie lines. So this is RE is the tie line. So you have to have a skill of drawing these tie lines. Draw the RE tie line, then you will get the YE here. This is the YE and this is XR. So YE and XR, two parameters you are finding out by drawing this equilibrium single stage diagram. So by drawing this equilibrium single stage diagram, you can able to find out YE and XR. Okay, once you find out YE and XR, you can take the help of this equation. E by R is equal to XM minus XR, you know XR, YE minus XM. So you know the YE, you can find out E by R ratio. So you have E plus R is equal to M and E by R is equal to this much. Then you can find out what is the E, what is R. So in that way, the quantities of E and R, the qualities of YE and XR can be estimated in a single stage extraction operation. This is how you have to find out. And yeah, I will just see for this case how to find out those things here. And see, initially you should have a idea that how much of minimum solvent should I add and how much of maximum solvent, because more than that solvent cannot give the good result. Okay, so how to find out that, that is how much minimum solvent you should have, because lesser than the minimum if you add, then there will be again homogeneous phase, and more than the maximum solvent requirement also gives the homogeneous phase. In between the minimum solvent and maximum solvent, these are the limits of the quantity of the solvent which can be used in the operation. So let us see that. So this is the binaural diagram which you have for a given system, because this is depending on the system. So you have initially the XF value, this XF value, at XF value draw the vertical line, then you will get the F here. So once you get the F, then S is the solvent, let us say pure solvent is added. So you will get Fs, that is the feed line. Then the feed line you can call it as. So M is resulted here. So M is resulted. In a normal condition, this is the tie line, because this is a tie line and this is another tie line, this is another tie line. So M is falling on this tie line. So only this R means this much of XR, this much of YE results. The vertical lines again gives the YE and XR. Okay, please understand carefully. Then how do you find out how much of minimum solvent is required? See, you have to just draw one tie line which goes to this point, because see, if M is very concentrated, how M can become very concentrated? If you add less quantity of the solvent, then M will become very concentrated. Then it goes up on this line, and comes to this point. This point. Once M is means if you reduce further S value, then it may crosses this binodal curve and goes to this one. So this is the homogeneous phase. It should not cross. So the maximum it can be reduced, solvent can be reduced to this value. So this value gives the XM minimum. This value gives the XM minimum, because a binodal one tie line is going through this one. So here in this case, XM minimum, this is the XM minimum, this is the XM minimum, and you know the YS XF value, then you can find out how much of minimum solvent is required, because per a taken 1 kg of the feed. So S minimum by F can be found out from this one by inversing the equation. So how much of solvent is required can be found out from these values. XF, XM minimum you can use, and also you can at XM minimum, this is the YE minimum. If you use this much of minimum solvent, then the raffinate will have this much concentration of the XM minimum, and extract will have YE minimum of this much concentration. So you can find out in this fashion what is the minimum solvent which do you require for the concentration of this much in the feed mixture to separate the solute for a given system of ABC can be estimated by using this equation and finding this one. And another limit, this is the lower limit of the solvent requirement, and another limit is maximum solvent requirement. See, if you go on adding the solvent, then the mixture will become very dilute. Dilute means C concentration reduces. So reduces. and comes to this point. And if you add more than this solvent, then it crosses to the heterogeneous to the homogeneous. This homogeneous zone is it won't separate. If you add this much of solvent, then it is possible. See, you will get one tile line here, and after that you won't get anything. So this may be called a pinch point. This is also called pinch point. So this gives the xm minimum. So if you replace xm minimum with xm maximum, then you will get the s maximum value, this one. So this gives the s minimum, this gives the s maximum. In between only the solvents can be used. So you can say that S minimum and X maximum does depend on the system as well as the feed composition. For example, feed composition is at this one, then you see you will be having again different values. So you can analyze that what does happen the solvent requirement if feed composition increases, and what does happen for the minimum solvent requirement if the system changes. The system may not be like this always, and tie lines may not be like this always. So it does depend on the system. So as a whole, for a particular system, by using the triangular diagram, you can able to find out the ranges of the solvent requirement, lower limit and higher limit. Minimum, maximum can be estimated. Hope that everybody is understanding this. Yeah. Similarly, you can use the right angle triangle diagrams where you can find out. See, this is drawn. The Xc is the concentration of the C in the raffinate, concentration of C in the extract. So you'll get this diagram, and again you can find out E and R. And similarly, you can also use solvent-free coordinates. Solvent-free coordinates. This is like a xy diagram. So you can draw n and xy. Again, you can draw. So what do you remember once you observe this particular operation? What do you? I think everybody can uh, remember the flash vaporization. In the flash vaporization, what did you see that if you add certain heat as a flash to the liquid mixture, then the quantity of vapor is generated and vapor and liquid will be in equilibrium. So the extract is analogous to the vapor, and raffinate is analogous to the liquid. They are getting divided. And now the solvent which you are adding, to the system is analogous to the heat. If you add the solvent to the feed mixture of A and C, then it makes the divisions into the extract phase and raffinate phase. If you add heat to the liquid mixture, so it separates vapor and liquid. So the single stage extraction is analogous to the equilibrium distillation, and where the heat is analogous to the quantity of the solvent, and the extract phase is analogous to the vapor phase, and raffinate is analogous to the raffinate liquid phase. So these are the further equations which will give you the so you can solve by using the ordinary diagram and nxy diagram, or the ternary diagram, whichever is easy for you. You can able to use that and find out the required uh, parameters, either quantities of the vapor phase, quantities of the liquid phase, or qualities of the extract phase and qualities of the raffinate phase can be estimated. So with the material balance and also the solute balance, you can able to do that. But however, you require the what you can say liquid phase diagram. And then if you use the multi-stage, multi-stage, there is an advantage. We'll see that what advantage does it have. So in a multi-stage, you can have either cross current or counter current operation. In a cross current operation, you can take stage 1, stage 2, stage 3. Here the total solvent which is available to you, for example, 10 kgs of the solvent is available. Instead of adding all the 10 kgs in a single stage, you can divide them into the 3 plus 3 plus 4, or 4 plus 3 plus 3, or 3 plus 4 plus 3, like that. Any combinations you can divide them into that, or 9 kgs can be equally divided, or 12 kgs can be equally divided, 4 4 4, like that, or anything you can able to do. Instead of adding all solvent at a time, you can add in a uh, different quantities in a different stages. That will give a lot of benefit in the operation, in terms of the consumption of the solvent wise, as well as for a given solvent you may get the maximum separation. So separation can be increased, or for a given separation the consumption of the solvent can be drastically decreased. So that will be very helpful. Instead of using all the solvent at a time, you can do in a stage wise. So the feed flows from stage to stage, and you are treating first. In the first stage, you are treating the feed with a small quantity of the solvent. Then you will get the extract here, and then the raffinate. In the raffinate, you have R1 quantity and X1 is the quality. It goes to the second stage. Then again, next batch of the solvent is added here. Then again, you will get the E2 and Y2, R2 and X2. So they are output quantities and qualities from the stage 2. Then you will be treating the whatever is coming from the stage 2 with another batch of the solvent, and in each batch of the solvent you have ys as a initial concentration, because whatever solvent is there, the solvent will have the same concentration, but you have divided into the 3 different batches. So again you will get E3Y3 and R3X3. So this R3X3 is the treated solution, that is called final raffinate, and E1, E2, E3 having Y1, Y2, Y3 will be collected, accumulated, and as a composited extract. So it will have total quantity of E1 plus E2 plus E3, but however the average concentration of Y1, Y2, Y3 in that. So in that way, composited extract is separated, and final raffinate will be obtained. So this is actually multi-stage cross current, because here the flows are perpendicular one to each. So you can call it as a multi-stage cross current operation. So both are moving in the opposite direction if it is a continuous operation. Then how do we find out here? In a similar way which you have done, see F and S, your F and S are added as a feed in a first stage. Then you will find out the mixture compositions with xm1. How do you calculate the xm1? Xm1 can be calculated f into xf into s into ys divided by f plus s will give the xm1. So on vertical line, on the fs line, the m1 point will be found out. Then now you have to draw one tie line which goes to the m1 point. Then you will get the E1 and R1. E1 is the extract from the first stage. R1 is the raffinate from the first stage. So this R1 is again treated with the same quality of the solvent. Yes. So R1 and S again added. So this is the mixture line for the second stage. Then the mixture point will slide down depending upon the solvent which you have added. So to the XM2, how do we find out XM2? XM2 can be found out R1 into X1 plus S into YS divided by R1 plus S will give the XM2. So vertical height of the that xm2 value on R1s line will give you the M2. Then you can draw R2 and E2. So when you draw the R2 and E2, then they are outputs of the second stage. Then again you can add these two and do like that. See, if you want to get this one in a single step, your M point should be where here. This M point should be here. Okay. So then you can calculate how much of the solvent is required for this. That is used by doing the three stages. You can reduce the quantity of the solvent such a fashion, and while you are doing some of the tutorial problems you can understand, and also you can wonder that the quantity of the solvent which can be reduced drastically will be higher multiples which is required in a single stage operation. So that can also be done by NXY diagram. This is the NXY diagram. This is the ternary diagram you can draw. So this gives the multi-stage operations. Now very important, which you can easily do the calculations by making an assumption that the feed solvent, what is the feed solvent? Is a F, and the solvent which you are using, that is organic solvent or extract solvent, both are completely insoluble in each other. So no B is entering here, but however it is taking a solute, and no E is entering into the B, however it is exchanging certain solute. So in that case, if you go on a this horizontal way, then R1 will be equal to A, R2 will be equal to A, R3 will be equal to A. So A is the quantity of the feed solvent except solute in the feed. F is having a what? A plus C. So it is only A quantities are not changing. Similarly, B quantities are not changing. B1 is entering and coming out, and B2 is entering and coming out, and B3 is coming and going and coming out. So B1, B2, B3 are not changing upon the dissolution of A. So the same B1 comes here, same B2 comes here, same B3 comes here. So in that case, we have to use the weight ratios. What are the weight ratios? Weight ratios are indicated with prime. X prime is X by 1 minus X. What is this? This is weight of C divided by weight of the non-C. For example, if the feed is having XF, XF as the weight fraction of the solute, then XF prime will be XF minus 1 minus XF. That means weight of the C divided by weight of A. It doesn't have any C in the denominator. So that's why X primes, Y primes are ratios. Again Y prime. YS is what? Weight of C divided by weight of the B. So B is the solvent in which we don't take. So Y prime is equal to Y by 1 minus Y. So in that way, you take instead of the weight fractions, if you take the weight ratios, then you can do the solute balance for the one of the tray here. Solute balance will give the A into X prime, B into Y prime, then the B into Y prime in that phase, and A into X prime. So this gives, so finally you will get A by Bn is equal to Ys prime minus Y prime by Xn minus 1 prime Xn prime. So it gives, suppose if you draw a drawing like a curve, equivalent curve between the Y prime and X prime, you will get XY diagram like this. So initially you have Ys prime in which Xf prime is there. So you can draw one operating line which will be having slope of A by B. This is the slope of A by B. Then you have X1 prime and Y1 prime. Y1 prime is the composition of the C in the extract which is coming out from the stage 1. And X1 is the concentration of the C which is coming out from the stage 1 as a raffinate. So x1 prime and y1 prime will be obtained. Then x1 prime is again treated with ys. This is a starting point. Then again minus a by b2. It is the slope of the second stage operating line. You can draw. Then you will get the y2 prime and x2 prime. Then again you can draw like this. So if you use the three stages, the finally raffinate will have this much concentration. Then the composited extract will have the average of this. Okay, you can find out how much of those things are there by doing the material balance. However, for example, in a single stage, if you want to achieve X3 as the raffinate composition, and your operating line should be like this. It should have a very slant operating line it should have. So what would be the slope of it? Minus a by b. So b is very high, then only it is a very low slope. Comparatively that the slope is very high. Now you calculate the b and compare with b1 plus b2 plus b3 and see that that is very high value. So which you can realize while you are doing the problems. So as a whole, what we can conclude that in a multi-stage cross-current operations, for the same separation, solvent consumption can be reduced instead of using the single stage. If you use the single stage, a lot of solvent is required. Instead of that, if you use three stages, then the solvent requirement will be reduced. Okay, so that is the benefit of having multi-stage cross-current operations. Okay. Similarly, if you come to the multi-stage counter-current extraction, multi-stage counter-current extraction, um, 1 minute. Multi-stage counter-current extraction. Acha.